Is this doing things? Hey, hello. Maybe? There we go, kind of. Audio working on Twitch? Yeah. Popping out chat in case we get some people. Right. Can you do things? God, I am tired, honestly. I usually am. Gotta apologize. Gonna be a weird thing. Of course, there we go. That's always gonna happen. Right. We are going for Chromie. Where were we? Honestly, I've kind of gotten where I was. What's going on? Exactly what we are doing. We were in smart pointers, I believe. Have we done this one yet? I don't know. Running code on cleanup with the drop trait. Drop trait. Yeah, we've done this. Takes out mutable reference to self to see when Muscov's drop. Yep, we've done the drop trait, absolutely. A little bit of a refresher for myself. The drop trait is a function which gets run when the smart pointer would be destroyed, usually at the end of whatever scope it's in. Yeah, we've already done this. And we got the, yeah, there we go. Right, the reference counted smart pointer. I don't think we've done this. Nope. No, we have not. This seems to be the place that we left off. Good to see, good to see. Right? Huh. Just a moment, I think we're going to start. Just gotta get one last thing done. I'm gonna mute my video. Show news video. There we go. Mute. I don't know what I'm saying. Again, incredibly tight. Alright, alright. Back on Xorg. X Wayland. Sorry, Wayland works for everything with the exception of Krita. Terrible time. Right, okay. 5 minutes in, I think this is where I will start. Good stuff, good stuff. It is Tuesday, right? Yes, good. I'm just going to start. I've said this before a million times. Don't know why I'm refreshing. Oh god, I cannot speak today. This is not going to be a good episode. Though nobody's watching, so that makes me a bit happier. Right, RCT, the reference counted smart pointer. In in the majority of events, ownership is clear. You know exactly which variables own a given value. However, there are cases when a single value might have multiple owners. For example, in graph data structures, multiple edges might point to the same node, and that node is conceptually owned by all of the edges that point to it. A node shouldn't be cleaned up until it doesn't have any edges pointing to it, and so has no owners. I'll admit I have no idea what that has to do. with graph data structures or what graph data structures are. You have to enable multiple ownership explicitly by using the Rust type RC type, which is an abbreviation for reference counted. The RC type keeps track of the number of references to a value to determine whether or not the value is still in use. If there are 0 references to the value can be cleaned up without any references becoming invalid. Imagine RC as a TV in a family room. When one person enters to watch the TV, they turn it on. Others can come into the room and watch the TV. When the last person leaves the room, they turn off the TV because it's no longer being used. Someone turns off the TV while others are still watching it. There will be an uproar from the remaining viewers. Also, there will be a use after free event, which would be a terrible thing. We use the RC type when we want to allocate some data on the heap for multiple parts of our program to read, and we can't determine at compile time which part will finish using the data last. If we knew which part would finish last, we could just make that part the data's owner, and the normal ownership rules enforced at compile time would take effect. Note that RC is only for use in single-threaded scenarios. When we discuss concurrency in Chapter 16, we'll cover how to do reference counting in a multi-threaded program. Okay, I was thinking RC might be useful for specifically a multi-threaded program, but I guess absolutely not. Using RC to share data. Right, so does this only work for immutable references, like in the TV scenario? Could I change the channel? Alright, let's return to our cons list example in listing 15.5. Recall that we defined it using box of a generic type. This time we'll create two lists that both share ownership of a third list. Conceptually, this looks similar to figure 15.3. So we have 3 and 4, or A and C, and A, sure, whatever. B, A, C. I don't know what this is showing, to be honest. I don't care either. Or I guess 2 lists, B and C, sharing ownership of a third list, A. Okay, so B and C. B on the third node owns a list called A, and C on the fourth owns a list called A, I guess. And the fifth node on A owns another list, which owns a nil value. No, this is a cons list. I see. No. Yeah, so it's a structure which has a value, and then separately a pointer to the next cons list. It's a con within a con within a con. I see now. Sorry, I forgot what this was. So within this cons list is a pointer to another con thing. Another con object, I want to say, but it's not an object, whatever. A con box, which holds both A value, and B, a pointer to the next cons item. Sure. We'll create list A that contains 5 and then 10. Then we'll make 2 more lists, B, that starts with 3, and C, that starts with 4. Both B and C lists will then continue on to the first A, list containing 5 and 10. In other words, both lists will share the first list containing 5 and 10. Trying to implement this scenario using our definition of list in box D won't work, as shown in listing 15.17. Right, so we have an enum with a list, cons, is the cons list. Use create list. Within the create context, the enum list, both cons and nil, the variance on list. We have main, let A equal new con with the value of 5. Secondarily, a box containing cons, a new cons object of 10, and a box with a new value called nil. B is 3, and a new box containing A, whereas C is 4, and a new box containing A, because B has ownership over, the box within B has ownership over A. C cannot utilize A to create a new box. The new box within cannot utilize A to create a new box. You can't take ownership. I believe this is what's happening. Or the exact place where the error may occur. Demonstrate we're not allowed to have two lists using blocks of any type that try to share ownership of a third list. When we compile this code, we get this error. We get this error. Right. Use of moved value A. We have the move occurs because A has a type of list which does not implement the copy trait. And the error exactly says, hey, the value is moved here, and you're using it after it is moved right here. Okay, the cons variant owns the data they hold. So when we create the B list, A is moved into B, and B owns A. Then we try and use A again when creating C. We're not allowed to because A has moved. And after B exits context, A will be destroyed. Meaning that if we still had C alive, it may attempt to use A when it is already gone. We could change the definition of cons to hold references instead, but then we would have to specify lifetime parameters. By specifying lifetime parameters, we would be specifying that every element in the list will live at least as long as the entire list. This is the case for the elements in lists and listing by 1517, but not in every scenario. Instead, we'll change our definition of list to RC of any type, in place of box of any type. As shown in listing 1518, each cons variant will now hold a value of an RC of any type pointing to a list. When we create B, instead of taking ownership of A, we'll clone the RC list that A is holding, thereby increasing the number of references from 1 to 2 and letting A and B share ownership over the data in that RC list. We'll also clone A when creating C, increasing the number of references from 2 to 3. Every time we call RC clone, the reference count to the data within the RC list will increase, and the data won't be cleaned up unless there are 0 references to it. So I'm assuming how this is implemented is that the clone implementation has been simply creates a new reference and then separately increases a counter within the RC within the wow, sorry, I cannot speak today. Yeah, simply increases a counter, and then separately the drop implementation decrements this counter. Right, so we got a list with the cons. We got the cons list right here. We are also adding in use standard RC and then the RC. Who knows what it is? Whatever. Let A equal RC new, and then we have within it the cons. Big cons list. We have cons for 5 and also a new cons, a new box with cons and a new RC with nil. Okay, so for everything within the original cons list, we also have to do this reference thing. Why? Why would not? Why would we not be able to just wrap all of this information within a singular RC? Would this delete? Would the new box be deleted at some point? Why do we need this? I'm curious what error will come out of this. What's the most recent day we got? Day 777. Who cares? Doesn't exist. Fantastic. Wow. Right, here we go. Right. What are we looking at here? These are not utilized. That's fine. I don't care. Right, so what if we simply take out this RC? Why would this cause an error? Mismatched types expected in RC list. Oh, because cons expects an RC list. I see. I'm an idiot. Which is fine. Alright. That's good information. Well, that was saved. I should unsave that. And it's gone, isn't it? Yeah. Alright. Yeah, I guess we did need to put in. Yeah, of course we did. We. No, not of course. Okay, you know what? I'm just gonna continue on. This is not helpful. We need to add a use statement to bring RC into scope because it's not in the prelude. In main, we create the listing to hold 5 and 10 and store it in a new RC list in A. That's sure. Then we create B and C. We call the RC clone function to pass a reference to the RC list in A as an argument. We could have called A.clone rather than RC clone reference A. Do we do that? I really didn't look at that. Yeah. But Rust convention is to use RC clone in this case. Why? The implementation of RC clone doesn't make a deep copy of all the data like most types implementations of clone do. Okay, because it's quicker and has less memory utilized. The call to RC clone only increments the reference count, which doesn't take much time. Deep copies of data can take a lot of time. By using RC clone for reference counting, we can visually distinguish between the deep copy kinds of clones and the kinds of clones that increase the reference count. When looking for performance problems in the code, we only need to consider the deep copy clones and can disregard calls to RC clone. Right, so A.clone would do the same as RC clone? If this is simply right, yeah, okay, I do understand. Right, so utilizing this syntax is just calling the same thing. A is an RC, and thus calling A.clone, utilizing the clone method in this way. Simply calls the same thing, doesn't really matter. However, using the syntax distinguishes it. Okay, that does make sense. Sorry. Uh, Cloning an RC increases the reference count. Let's change our working example in listing 1518 so we can see the reference count changing as we create and drop references of RC list in A. In listing 1519, we'll change main so it has an inner scope around C. Then we can see how the reference count changes when C goes out of scope. Let A equal a new RC, holding clone, con, holding a new cons item, holding 5, and a new RC, holding set cons list, etc. Right? Let B equal the same, just 3 and a RC clone of A. We are just strong count, sure. What? Fuck off. Sure, yeah, I guess. Whatever. We're now utilizing strong count. Don't know what that means. Hopefully it'll explain. At each point in the program where the reference count changes, we print the reference count, which we get by calling RC strong count. This function is named strong count rather than count because the RC type also has weak count. We'll see what is used for in the preventing reference cycles turning an RC into a weak section, which is later on in this chapter. What does strong count do? Yeah, it's just getting the count, I guess. That's fair. Could we call a dot strong count? I don't see why not. We probably no, we may not be able to do that. That's fair. That's understandable. Yeah, I don't think we could. Maybe we can though. Who knows? I could see an implementation where we absolutely could, but also entirely possible that we can't. Who knows? Who cares? I really am curious what these two things are, but we'll learn in a little bit of time. All right, this is just going to output count the amount of references, and then after we delete C, we'll see that there are still two in count, and we can't utilize C instead. Wow, I'm really descriptive today. You can see that the RC list in A has an initial reference count of 1. Then each time we call clone, the count goes up by 1. C goes out of scope, the count goes down by 1. We don't have to call a function to decrease the reference count like we have to call RC clone. We don't have to call a function to decrease the reference count like we have to call RC clone to increase the reference count. Sometimes it's me being terrible at reading, but sometimes it's just the terrible wording. Honestly, that's not a well-structured sentence. Though, I mean, how can I complain? You guys have heard me through this entire section. The implementation of the drop trait decreases the reference count automatically when an RC value goes out of scope. What we can't see in this example is that when B and then A go out of scope at the end of main, the count is then 0, and the RC list is cleaned up completely. Using RC of any type allows a single value to have multiple owners, and the count ensures that the value remains valid as long as any of the owners still exist. Via immutable references, RC allows you to share data between multiple parts of your program for reading only. If RC allowed you to have multiple immutable references too, you might violate one of the boring rules discussed in Chapter 4. Yep. Is there any way to do this with mutable data? Yeah, it creates data races and inconsistencies. But being able to mutate data is very useful. In the next section, we'll discuss the interior mutability pattern and the ref cell type that you can use in conjunction with RC to work with this immutability restriction. Okay, that was a task. Determine whether it'll pass and what it'll do. Alright, so we got RC new 1. We have an RC with a value 1 inside of it, which is n. We have let mutable n2 equal RC clone reference n. Right, the data inside of it cannot be mutable. However, this could perhaps have a mutable. I really don't see this directly being a problem. I see what's next. I think that'll be a problem, but you know, the let mute n2 I don't think is the issue here. We have RC clone n, which means that we have n2, which is a mutable variable, and inside of this immutable variable, you have RC clone reference to n. So here we could change what it is referenced to, but we cannot change the value of n. We dereference n2 and then add 1. This will not work, however, because we cannot mutate the value n2 has. I mean, I don't think this is just a reference to I believe in this case, RC would be just a reference. The dereference of RC would be the reference to n here, correct? No, no, 1. We are just cloning n. So dereferencing, so this would just be n. I'm an idiot. Yeah, this would just be n. RC clone is not creating a new RC, it is simply cloning an old one. I'm an idiot. Yeah, so no, this is getting the value, and that's not gonna work. We can't have a mutable reference to an immutable thing either. That wouldn't work either. This will also error out. I'm pretty certain. I'm wrong about my previous understanding. Determine whether the program will pass the compiler. If it passes, write the output as if it were executed. We got a struct example implementing drop. For example, we have a function called drop. It takes a reference, immutable self. It just prints drop. I see no issue with this. All right, let x equal a new RC holding example. an empty example struct, which is fun. Then we have y, which is RC clone x, and increases the count by 1, and that's fine. We have print line a, then we have drop x. That's fine, I believe. I see no reason why that wouldn't be okay, since it is an RC. It'll simply decrement the count. We have not dropped example, however. Not yet. So it will be a, drop x, x will be dropped. X is an RC, of course. Example still exists within y and has not been dropped. We will then print b. Our response so far is a, b. Then we will drop y. Y is dropped, the RC is dropped. It is decremented from 1 to 0. And example within the RC that is within y will also be dropped, meaning that this will run. The function drop will print drop. Drop. Then we get C. I see no issues on why this wouldn't compile. Example is dropped between B and C. Submit. Got it all correct. Let's get some context. Context. Data inside an RC cannot be mutated without the use of interior mutability. See next section. RC enforces this property by implementing the deref trait, but not implementing the deref mute trait. Okay. Here it's just saying the value inside a reference counted pointer is only ever dropped once, so drop is only printed once. So your initial drop decrements the reference count, but does not drop the value because y still is alive. Then dropping y finds that the reference count is 0 and drops example. Fantastic. I thought I misspelled something, honestly. Right, so we got a ref cell and an interior mutability pattern. Interior mutability is a design pattern in Rust that allows you to mutate data even when there are immutable references to that data. Normally, this action is disallowed by the borrowing rules. To mutate data, the pattern uses unsafe code inside a data structure to bend Rust's usual rules that govern mutation and borrowing. Unsafe code indicates to the compiler that we're checking the rules manually instead of relying on the compiler to check them for us. We discuss unsafe code more in Chapter 19. Not even close to that, are we? Nah. We can use types that use the interior mutability pattern only when we can ensure that the borrowing rules will be followed at runtime, even though the compiler can't guarantee that. The unsafe code involved is then wrapped in a safe API, and the other type is still mutable. Let's explore this concept by looking at the ref cell type that follows the interior mutability pattern, enforcing borrowing rules at runtime with ref cell. Unlike RC, the ref cell type represents single ownership over the data it holds. Right, so what we're going to have is a reference to ref cell instead of a reference to a piece of data. So that makes ref cell different from a type like box T. Recall the borrowing rules you learned in Chapter 4. At any given time, you can have either, but not both, one mutable reference or any number of immutable references. So we'll have a bunch of immutable references to the ref T, which will be a mutable reference. So a dereference to the ref cell, sorry, not ref T, and then the data itself is immutable. References must always be valid. When referencing a box, the borrowing rules invariants are enforced at compile time. With ref cell, these invariants are enforced at runtime. Okay, maybe I'm wrong. With references, if you break these rules, you get a compiler error. With ref cell, if you break these rules, your program will panic and exit. That's much worse. Advantages of checking the borrowing rules at compile time are that errors will be caught sooner in the development process. There is no impact on runtime performance because all of the analysis is completed beforehand. For those reasons, checking the borrowing rules at compile time is the best choice in the majority of cases, which is why this is Rust's default. The advantages of checking it at runtime instead is that certain memory safe scenarios are then allowed, where they wouldn't have been allowed by the compile time check. Static analysis like the Rust compiler is inherently conservative, Some properties of the code are impossible to detect by analyzing the code. The most famous example is the halting problem, which is beyond the scope of this book, but an interesting topic to research. I'm sure it's a pretty easy problem to solve, just figure out if something will in fact end. Seems easy. Because some analysis is impossible, if the Rust compiler cannot be sure the code compiles, with the ownership rules, it might reject the correct program. In this way, it's conservative. The halting problem is checking to see if the program will run incomplete without failing. If Rust accepted an incorrect program, users wouldn't be able to trust in the guarantees Rust makes. However, if Rust rejects a correct program, the programmer will be inconvenienced, but nothing catastrophic will occur. The ref cell type is useful when you're sure your code follows the boring rules, but the compiler is unable to understand and guarantee them. Similar to RC, refcell is only for use in single-threaded scenarios, and will give you a compile time error if you try using it in a multi-threaded context. We'll talk about how to get the functionality of refcell in a multi-threaded program in Chapter 16. Next chapter, Fearless Concurrency. That's a good name. Here's a recap of the reasons to choose Box, RC, and refcell. Can we have some examples of refcell? Oh, okay, we got a lot more. So hopefully. RC enables multiple owners of the same data. Box and refcell have single owners. Box allows immutable or mutable borrow check at compile time. RC allows only immutable borrows checked at compile time. Refcell allows immutable or mutable borrows checked at runtime. Because refcell allows mutable borrows checked at runtime, you can mutate the values inside of the refcell even when the refcell is immutable. Mutating the value inside of an immutable value is the interior mutability pattern. Mutating the value inside an immutable value is the interior mutability pattern. Let's look at a situation in which interior mutability is useful and examine how it's possible. Right, so again, I'm guessing you're going to have an immutable reference to a ref cell, which is in and of itself mutable. Or the value within is mutable. So, interior mutability, immutable borrow to an immutable value. Or I guess the opposite? I don't know, whatever. A consequence of the borrowing rules is that when you have an immutable value, you can't borrow it mutably. For example, this code will not compile. So you have x, which is 5, and y, which is a mutable reference to x. Can't do that. If you try to compile this code, you get the following error. Not borrow x as mutable, as it is not declared as mutable. Yep. However, there are situations in which this could be useful for a value to mutate itself. There are situations in which it would be useful for value to mutate itself in its methods, but appear immutable for other code. Code outside the value's methods would not be able to mutate the value. Using refcell is one way to get the ability to have interior mutability. But refcell doesn't get around the borrowing rules completely. The borrow checker in the compiler allows this interior mutability, and the borrowing rules are checked at runtime instead. If you violate the rules, you get a panic instead of the compiler, meaning your application crashes in the hands of a client. Let's work through a practical example where we can use refcell to mutate an immutable value and see why that is useful. A use case for interior mutability. Mock objects. Sometimes during testing, a programmer will use type in place of another type in order to observe particular behavior and assert it's implemented correctly. This placeholder type is called a test double. Think of it in the sense of a stunt double in filmmaking, where a person steps in and substitutes for an actor to do the particularly tricky scenes. Test doubles stand in for other types when we're running tests. Mock objects are specific types of test doubles that record what happens during a test, so you can assert that the correct actions took place. Rust doesn't have objects in the same sense as other languages have objects, and Rust doesn't have mock object functionality built into the standard library as some other languages do. However, you can definitely create a struct that will serve the same purposes as a mock object. Like a lot of other languages, it's not object oriented in the way that it has it built in. You can't just build an object, but you can build something which follows the paradigm of object orientation. Yeah. Here's the scenario we'll test. We'll create a library that tracks a value against a maximum value and sends messages based on how close to the maximum value the current value is. This library could be used to keep track of the user's quota for the number of API calls they're allowed to make, for example. A library will only provide the functionality of tracking how close to the maximum value is and what the messages should be at what times. Applications that use a library will be expected to provide the mechanisms for sending the messages. The application could could put a message in the application, send an email, send a text message, or something else. The library doesn't need to know that detail. All it needs is something that implements a trait will provide called messenger. Listing 1520 shows the library code. We have a trait called messenger, function send, public struct, limit tractor, which holds messenger, a reference with lifetime a to any type, value, which is a usize, and a max, which is a usize. Right, so implementing with lifetime a and generic type t, limit tractor with lifetime a and generic type t, where t is of type messenger. Yeah, that's a trait, where t is the trait messenger, or implements the trait messenger. Okay. Public function new, uh, taking in messenger, which is a reference with a lifetime of a of any type, and max, which is a usize. Outputting a limit tracker with the same lifetime and type. All right, and then we simply output limit tracker. Messenger is the messenger value. Value is 0, and max is just max from the original. Function set value, which is public, takes an immutable reference to self. It is still within the implement block, I believe. Yep. Also taking in a value. That's just for the set value. Yep. Self.value equals the new value, like percentage of max equals self.value as a 64-bit float divided by self.max as a 64-bit floating point. Yeah, that's correct. If it's greater than or equal to 1, you are over your quota. Okay? Okay, sure. Do we need? Oh, no, there's no issue with this. Yeah, that's fine. Self.messenger.send. You are over your quota. Then we just say if you're under it, there's a warning. You got 90% of your quota. If you are using 90%, 75, you are, yep, another warning saying you're 75% over your quota. Otherwise, do nothing. Right, so one important part of this code is that the messenger trait has one method called send that takes an immutable reference to self and the text of the message. This trait is the interface of our mock object needs to implement so that the mock can be used in the same way a real object is. The other important part is that we want to test the behavior of the set value method on the limit tracker. We can change what we pass in for the value parameter, but set value doesn't return anything for us to make the assertion on. We want to be able to say that if we create a limit tracker with something that implements the messenger trait and a particular value for max, when we pass different numbers for value, the messenger is told to send the appropriate messages. We need a mock object that, instead of sending an email or text message when we call send, will only keep track of the messages it's told to send. we can create a new instance of the mock object, create a limit tracker that uses a mock object, call a set value method on set our limit tracker, and then check that the mock object has the messages we expect. Listing 1521 shows an attempt to implement a mock object to do just that, but the borrow checker will not allow it. All right, so we got mod tests using super, bringing in everything from the previous module's context. We have struct, mock object. We're making a struct called a mock messenger, which holds sent message, just a vector of strings. Implement mock messenger, function new. The new method within mock messenger outputs mock messenger, a mock messenger struct. Implementing on the mock messenger struct the function new, which outputs mock messenger. We create a mock messenger with the send message value of an empty vector. Implementing messenger for mock messenger in order to satiate the necessity for the send trait on a messenger. Right, we have send, which takes in a reference to self, immutable, sorry. The message, which is simply a reference to a string. Self.sendMessenger.push string from message, which is brought in here. Right. We then have the test. It sends an over 75% warning message. Let mock messenger equal mock messenger new. Let mutable limit tracker equal limit tracker new mock messenger reference to the mock messenger created here, which is empty, and 100. Right, limit tracker with the mock messenger reference to this mock messenger, which is empty, sure. And 100, that's good. We have limit tracker dot set value 80. Assert equal mock messenger dot sent message dot length is 1. Okay. Why won't this work? I cannot track what's going on, to be honest. Right, I believe that this will not work because we are attempting to push to the self.send messages this string. I don't know. What is the error? Let's just read forward. This test defines a mock messenger struct that has a sent messages field with a back of strings value to keep track of the messages it's told to send. We also define an associated function new to make it convenient to create new mock messenger values that start with an empty list of strings. We then implement the messenger trait for mock messenger so we can give a mock messenger to a limit tracker. In the definition of the send method, we take the message passed in as a parameter and stored in the mock messenger list of sent messages as a reference, correct? Well, it's a reference string. That's a string slice. But we have a string from this string slice, so I think that's copied over. I don't think that's a reference at all. In the test, we're testing what happens when the limit tracker is told to set value to something more than 75% of the max value. First, we'll create a new mock messenger, which will start with an empty list of messages. Then we create a new limit tracker and give it a reference to the new mock messenger and a max value of 100. We call the setValue method on the limit tracker with a value of 80, which is more than 75% of 100. Then we assert that the list of messages that the mock messenger is keeping track of should now have one message in it. Here, there's a problem in the test, as shown here. Right, cannot borrow self.sentMessages as mutable, as it is behind a reference. Right. We have self and string message. Let's consider changing that to be mutable reference at mute self. Okay, so we can't borrow self here because it's immutable. And then we try and mutate it here. Yeah, that's reasonable. Yeah, we can't mutate a mutable reference. self is just a reference, so the data it refers to cannot be borrowed as mutable. We can't modify mock messenger to keep track of the messages because the send method takes an immutable reference to self. We also can't take the suggestion from the error text to use a mutable reference to self instead, because then the signature of send would not match the signature of messenger trait definition. Feel free to try and see what error message you get. Yeah, of course not. This is a situation in which interior mutability can help. We can store the sent messages within a ref cell, and then the send method will be able to modify sent messages to store the messages we've sent C. Listing 1522 shows what that looks like. Right, so where exactly have we changed this? Right, yeah, so within the struct mock messenger sent messages is now a ref cell of type vector of type string. Is this the only thing we've changed? No. Well, of course we'd have to change this, because we now need a ref cell. Where else? Right, so within the send function, we have a reference to self, self.sendMessages, .borrow mutable. Alright, so borrow mutable is a function on ref cell, which we then push the string to. Okay, so we can still have an immutable reference to the ref cell, however, the method borrow mutable or borrow mute on ref cell will, I assume, allow you to mutably borrow the vector inside of here, which then we can push string from message to. Right? And this will all work. That'll work fine. The sent message field is now of type ref cell, holding a vector, which holds a string value, or string values, instead of simple vector strings. In the new function, we create a new ref cell vec string instance around the empty vector. Oh, sure. For the implementation of the send method, the first parameter is still an immutable borrow self, which matches the trait definition. We call borrow mute on the ref cell vector string, and the self.sendMessages to get immutable reference to the value inside of ref cell vector string, which is the vector. Then we can call push on the mutable reference to the vector to keep track of the messages sent during test. The last change we have to make is in the assertion. See how many items are in the inner vector. We call borrow on the ref vec string to get an immutable reference on the vector. Oh, I didn't notice that. I didn't read it. Alright, so mock messages.sendMessages.borrow.length. Okay, so yeah, that does make sense because send messages, by my understanding, should be the ref cell. So we can't call length on the ref cell. It may not have that implemented, of course. So we need that vector. Meaning we need to borrow the contained vector in order to get that length. 1. I'm assuming that's what it is. It doesn't explicitly say notice. Alright. Now that you've seen how to use refcell, let's dig into how it works, keeping track of borrows at runtime with refcell. When creating immutable and mutable references, we use the reference and reference immutable syntax, respectively, with refcell. With refcell, we can use borrow and borrowable mute methods, which are part of the safe API that belongs to refcell. The borrow method returns the smart pointer type ref t. Oh. Okay. And borrow.mute, borrow_mute, returns the smart pointer type ref mute, any type. Both types implement deref, so we can treat them like regular references. Okay, I was wrong. Kinda. No, I was pretty much wrong. The ref cell keeps track of how many ref and ref mute smart pointers are currently active. Each time we call borrow, the ref cell increases its count of how many mutable borrows are active. When a ref value goes out of scope, the count of immutable borrows goes down by 1. Just like RC. Just like the compile time borrowing rules, refcell lets us have many immutable borrows, or 1 mutable borrow at any time. If we try to violate these rules, rather than getting a compiler error as we would with references, the implementation of refcell will panic at runtime. Listing 1523 shows a modification of the implementation of send in listing 1522. We're deliberately trying to create 2 mutable borrows active for the same scope to illustrate that ref cell prevents us from doing this at runtime. Right? Yep. We just call borrow mute twice. We create a variable borrow. Sorry, we create a variable one borrow for the ref mute smart point to return from borrow mute. Then we create another mutable borrow in the same way in the variable to borrow. This makes two mutable references in the same scope, which isn't allowed. When we run the test of our library, yep, it doesn't work. Notice that the code panicked with the message already borrowed mute error. This is how RefCell handles violations of the borrowing rules at runtime. Choosing to catch borrowing errors at runtime rather than compile time, as we've done here, means you'd potentially be finding mistakes in your code later in the development process, possibly not until your code was deployed into production. Very bad. Also, your code would incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than compile time. However, using RefCell makes it possible to write a mock object that can modify itself to keep track of the messages in a scene while you're using it in a context where only immutable values are allowed. Wow. You can use RefCell despite its trade-offs to get more functionality than regular references provide. Right. How much do we have left? I am going to leave much earlier than I probably want to. You know what? Honestly, I think I'm just done for today. I'm not really absorbing information. It's not a good day for me, I guess. Hey. Well, that'll be it for now. Goodbye.